Very good morning, my dear friends. Myself, Dr. M.H. Annaya, and in today's video, we are going to work out a problem on a flat steel plate with a circular cutout. There is a circular hole drilled at the center, subjected to a pull. Friends, you know, stress concentration is defined as the accumulation of stress at a discontinuity. It could be a hole, a notch, or sudden change of cross section from a bigger dimension to a smaller dimension. So all this will lead to the accumulation of stress and result in early failure of the component. Now let us work out a problem on a flat plate which is subjected to a pull. Friends, the question for today's video runs like this. A steel plate 50 wide and 5 thick with a hole of diameter 10 drilled at its center. So first of all, we'll write down the sketch of that plate. So friends, we have a plate here and they have given the dimensions of the plate, and there is a hole drilled exactly in the center, and the diameter of that hole is given to be 10 millimeter, and this is represented in the handbook, machine design handbook, as D, and the width of the plate we will call it as B, is the width of the plate. And this cross section, if you see, it is having a rectangular cross section. I'll write down here only, and the thickness of the plate is given to be 5 millimeter. 5 millimeter, and it is subjected to a pull. So we'll call this as F, an axial pull of what's the magnitude? 1 kilonewton. 1 kilonewton, which is equal to 1000 Newton. And the hole diameter is given, and the width of the plate B is given to be 50 millimeter wide, that is 50. And this is the data, friends. Now it is subjected to a pull of 1 kilonewton. Friends, what happens if there were no hole drilled in the plate? You would have got the tensile stress due to the pull 1 kilonewton as load over area, that is 1000 divided by area of cross section, that is 50 into 10. That would have been the answer. What happens because of the presence of this hole? The stress gets accumulated here, and the value of the stress induced will be more than the nominal stress. So friends, what happens now? We are required to find out the maximum stress induced in the member. The question that is being asked is sigma max, that is maximum stress induced in the member. Now friends, we have a term called stress concentration factor, which is defined as K sigma, that is the stress concentration factor, SCF, that is equal to the maximum stress to the nominal stress. This is the formula for the stress concentration factor K sigma. Now friends, for axial load, this is the formula sigma tensile max by sigma nominal, and if it is the case of a bending, we use the same notation and say it is sigma B max, bending stress maximum value, divided by sigma B nominal. Similarly friends, if it is the case of a torsion, we have K sigma, that is K tau we call, is tau maximum, means maximum shear stress, divided by nominal shear stress, is the formula that are being used. So friends, in today's problem, we are going to apply this formula because this is the case of a member subjected to tensile load. So friends, we will start with the formula, that is K sigma is equal to sigma max by sigma nominal. We are interested in finding out what is sigma maximum. Therefore, sigma maximum is equal to K sigma multiplied by sigma nominal. So friends, to find out this quantity, so we need to have what is K sigma and what is sigma nominal. So we have to find out these two parameters to get the value of the maximum stress induced in the member. Friends, now to find out K sigma, you will have to refer to the machine design data handbook on the chapter stress concentration. And friends, there will be a graph like this, wherein the value of K sigma is plotted along the y-axis. The ratio of d by b or d by w, the width d by b, is plotted along the x-axis. Friends, different authors make use of different formulae for notation. For example, here for width, some authors represent as w and this diameter as a. It is one and the same. So friends, you have a graph like this. If you see the graph wherein the plate will be given like this with the load, and this is the curve how the stress concentration factor varies along with d by b. So friends, for the given plate, if you are able to find out what is d by b ratio, at that value of d by b, you can write a vertical line to touch this curve here and read the value of K sigma, the stress concentration factor on the y-axis. Friends, here let us see what is d by b for the given plate. For the given plate, d by b is equal to, d is the diameter of the hole, that is 10 millimeter, and b is the width of the plate, that is given to be 50 millimeter. So 10 by 50 works out to 0.2. So on the x-axis in the graph, there is a plot of d by b. So exactly at 0.2 value along the x-axis, write a vertical line to touch this curve at this point. From there, write a horizontal line. And friends, for this value, if you refer to the machine design data handbook, you will be able to get the value of K sigma. I can say for d by b equal to 0.2, from the MDH, we get K sigma is equal to 2.5 exactly. 2.5 is the value. So we are able to find out what is the value of K sigma. Let us see what is sigma nominal. So I will just clear this. Friends, now we have to find out what is sigma nominal. Friends, sigma nominal, that is nominal stress, is equal to the load divided by the area of cross section. Area of cross section at whole. It is along the cross section of that. So this is given by F divided by area of cross section. The total width is B, we have taken minus D. B minus D into H is the area of cross section of the plate. And friends, in the same graph, if you see, they will put this sketch like this. They will put this hole there and show all these. and they'll also give you what is K sigma, that is equal to. All this you find on the graph itself. Sigma max divided by sigma nominal. So there is no need to remember any of this, but you should be able to identify where the graph is and which graph you will have to refer. It all depends on the type of problem or the component you have got. Friends, F is the load. The load the member is subjected to, that is 1000 Newton, 1 kilonewton. And B value, we know it is 50 mm. The value of the diameter is 10 mm. Diameter of the hole is 10 mm. And H is equal to 5 mm. So we have to substitute in the formula these values to find out sigma nominal. So I will just put the value as 1000 divided by B minus D. B is width of the plate, D is diameter 10 mm, and the thickness of the plate H is 5 mm. And friends, if you simplify, this is 1000 divided by 40 into 5, 200. It works out to 5 Newton per mm square is the value of the nominal stress. Friends, we know the nominal stress, we know the stress concentration factor, and hence we will be able to calculate the value of sigma max. Therefore, sigma max is equal to K sigma, is the stress concentration factor, multiplied by sigma nominal. So friends, this we have got from the graph as 2.5, and the value of sigma nominal just now we have calculated as 5. And friends, this works out to 12.5 Newton per mm square is the value. That is the sigma maximum. Friends, I hope the presentation was interesting, and I make a small request to you. Whenever you are seeing this video, please go through the complete video without fail. Then I also request you to make some criticism or appreciation as you like, depending on the video you see. And this will help me, and this will act as a motivator and help me to make more and more videos. Thank you friends for watching my YouTube video, and I wish you all best of luck.